Alrighty then, folks. I'm going to, whoopsie, freak out a little bit, and then I'm going to not freak out a little bit, and I'm going to get straight back on it. Car accelerates at a constant rate of 1.83 meters per second squared. Along a flat straight road, the force acting on the car is 1.870 kilonewtons. Calculate the mass of the car. Give your answer to 3 significant figures, and it wants the answer in kg. So I've got to bring this down. I've got to bring this back to base units. So it's a kilo. So I'm going to multiply that by 10 to the 3, which is going to give me the actual number that I need. The equation that I need in it, fam, mush, wagwan, F is equal to A times M, divide across by A to get the M as the subject of the equation. I'm going to put 1.87 times 10 to the 3 divided by 1.83, which will give me my mass. And the answer for that question is 1.87 times 10 to the power of 3 divided by 1.83 equals 1021. Is equal to 1021.86, and I can just put that down. And I need to put that to 3 significant figures, so I'm going to count 1, 2, 3 significant figures, give me an answer of 1020. The car accelerates from rest, so its initial velocity is 0 meters per second. Its final velocity is, I do not know, meters per second. The amount of time needed for that is 16 seconds, and it accelerates at 1.83 meters per second squared. Always be aware when there are numbers in the question above, because you might get confused and not put the right numbers in. So I should write down my equation. Acceleration is v minus u divided by t. Acceleration is equal to v. Oh, pardon me, I've messed that up as well, haven't I? I'm trying to find v. I'm going to substitute first, and then I'm going to rearrange. I'm going to do 1.83 is equal to v minus 0 divided by 16. Multiply across by 16. 1.83 times 16 is equal to v. I don't have to do any changing around of anything. It doesn't need any special significant figures. It is just going to give me my answer as 29.28. And there is 2 decimal places there, so I'll leave it as 2 decimal places there as well. The espresso machine shown in figure 27 is an electrical appliance. It has an electrical heater connected to 440 volt main supply. Voltage equals 440 volts. And the power of the electrical heater is 3.5 kilowatts. Power is equal to 3.5 kilowatts. It's not telling me what units to put in down here, so I'm going to multiply that by 10 to the 3 to make it up to watts. Before the espresso machine can be used, this heater must raise the temperature of some cold water. The specific heat capacity of water, C, is equal to 4,200 joules per kilogram Kelvin. That's strange. All right, there we go. Show that it takes the heater about 90 seconds, so the time should be about 90 seconds to raise the temperature of 1 kilogram of water from 18 degrees Celsius to 95 degrees Celsius. The mass of the water equals 1 kilogram, and we're going to find out the delta theta, which is 95 take away 18. 95 take away 18 is 77 degrees Celsius. All right, this is an interesting one. So, what have I got? What have I got? What have I got? Well, first off, I need to find out the amount of energy needed to raise the temperature of 1 kilogram of this substance by this amount of a temperature change. And to find that, I need to use E is equal to M times C times delta theta. That will tell me the amount of energy that's necessary to raise the water inside. So I shall say that energy is 1 times 4,200 times 77. Pop that into my equation. 1 times 4,200 times 77 is equal to 323,400 joules. That's the amount of energy that's needed. Now, how am I going to know that? How am I going to figure out if it takes 90 seconds or not? Well, the power is 3.5 kilowatts, and 1 watt is equal to 1 joule per second. So 3,500 watts is equal to 3,500 joules per 1 second. So if I divide my 332,400 by 3,500, that will tell me the amount of seconds necessary. The amount of seconds are needed for that amount of energy to be transferred. Now, this is assuming 100% efficiency, of course, which isn't 100% true, but there you go. That divided by that gives me a time of 92.5 seconds, which is around 90 seconds. Tricky little question that, and well worth 3 marks in a higher tier paper. But how do we get to this? How did I get to that? Well, I wrote down all my numbers. I wrote down everything that I've got. And it was asking me about this heater having to do something. And the heater is obviously going to use energy. And it also gave me this power. And it gave me this voltage. I don't know why it gave me the voltage. I mean, there could have been another way of doing that, I suppose. It was Q times V, possibly QVT. No, I don't think so. This was the bit here that will probably get you a last mark. But that kind of question, if you write down everything you have a look at what you can use, have a look at what fits where, and then you'll be sorted. The diagram shows a bullet moving towards a wooden block. Not a happy little block. The bullet is moving at a velocity of 170 meters per second. The mass of the bullet is 0.03 kilograms. Show that the momentum of the bullet is around about, is it 5.0 kilogram meters per second. Momentum is equal to mass times velocity. Momentum is equal to 0.03 times 170. Momentum is equal to 5.1. So the momentum is 5.1 kilogram meters per second, and that is about that. The bullet collides with the wooden block and sticks in it. Ooh, the bullet and the wooden block move off together. The mass of the wooden block is 0.8 kilograms. Calculate the velocity of the wooden block immediately after the collision. All right, so to know this, we need to know that momentum 1 is equal to momentum 2. The momentum before is equal to the momentum afterwards. Now, we've worked out that this bullet has got 5.1 kilogram meters per second of momentum, and that my wooden block, because it's not moving, has got 0 kilograms per meter second. So that means that the total momentum, E1, is equal to 5.1 kilogram meters per second. Now, afterwards, the total momentum will still be the same. So I can say that P1 is equal to P2. Completely lost my train of thought here. The wooden block with the mass of the wooden block. Yeah, okay. So I need to find out the momentum afterwards. So my wooden block and my so I need to find the mass total, and that will equal to the mass of the block plus the mass of the bullet. Oh, not the bullet. Plus the mass of the bullet. So I'll have U for bullet and B for block. And I'll find that by adding the mass of the bullet, 0.03, with the mass of the block, 0.8. So 0.8 kilograms plus 0.03 kilograms gives me a total mass of 0.83 kilograms. P1 is equal to P2. The momentum before is equal to the momentum afterwards. P1 is equal to the total momentum at the top, 5.1 kilogram meters per second. And I can figure out the velocity of this second, this resultant momentum if I use these numbers. So P1 is equal to P2, 5.1 kilograms meters per second, or 5.1 kilogram meters per second, is equal to the mass of the total mass multiplied by the velocity of the two, and that's what I'm trying to find. So I'll divide across by total mass. 5.1 over total mass is equal to the new velocity. Get rid of that and I'll put my numbers in. 0.83 is equal to velocity. 5.1 divided by 0.83. 6.144. Velocity is equal to 6.144 meters per second. So total momentum before equals total momentum afterwards. P1 is equal to P2. I knew what P1 was, so I can use that as one of my variables. But the mass has changed because they're stuck together. The wooden block and the bullet are now stuck together. So I have to find the new mass first off. My mass multiplied by my new velocity will equal 5.1 because the total momentum at the start is equal to the total momentum at the end. And then I just had to do normal switcheroo. Calculate the minimum total energy of the photons produced when an electron and positron collide. Use the equation E is equal to mc squared. Cool. Mass of an electron, m, is equal to 9.1 times 10 to the minus 31 kilograms, and the speed of light, c, is equal to 3.0 times 10 to the 8 meters per second. The photons produced when an electron and a positron collide. Use the equation, mass of an electron. All right, well, I'm just going to assume that we're looking at the mass of the electron. Minimum total energy, I'm just going to be looking at photons. I'm just going to be looking at 1. So I shall substitute in my numbers. E is equal to 9.1 times 10 to the minus 31 multiplied by 3.0 times 10 to the 8 squared. And I'm just going to put that into a calculator. because I think nobody got time to do that in their head. 9.1 times 10 to the power of minus 3? No, minus 31. Times 10 to the power of minus 31 multiplied by 3.0 times 10 to the power of 8, close bracket, squared. Golly, that's a big number. The amount of energy produced is 8.19 times 10 to the minus 14. Considering that it's an electron, that's a lot of energy. All right. Yep. Next question. The ball. Demolition ball has got a mass of 400 kilograms. Let's zoom in a tiny bit here. So the mass is 400 kilograms. And it moves from point A to point B, moving through a vertical height of 1.5 meters, h equals 1.5 meters. Calculate the change in gravitational potential energy, delta EP is equal to, I do not know how many joules. Take gravitational field strength, G is equal to 10 newtons per kilogram. Write down my equation, EP is equal to M times G times delta H. EP is equal to 1.5, oh, it's not, it's equal to 400 times 10 times 1.5. EP is equal to 400 times 10 times 1.5, 6,000 joules. Question 32. Pilot begins to land an aircraft. Ooh, scary. The height of the aircraft decreases from 2 meters above the ground to 1 meter. So delta H is equal to 100 meters. 200 meters take away 100 meters, which is equal to 100 meters. The velocity of the aircraft when it lands is 75 meters per second. It's fast. The mass of the aircraft mass is 130,000 kilograms. Calculate the momentum of the aircraft. Momentum is equal to, I do not know how many kilogram meters per second. But I know my equation is momentum is equal to mass times velocity. Momentum is equal to 130,000 multiplied by 75. Momentum is equal to 130,123 multiplied by 75. And that gives me 9.9,750,000 kilogram meters per second as the momentum. The aircraft comes to a stop. State the momentum change of the aircraft from when it lands to when it stops. Oh, sorry, everyone. It's come out. Okay, now it's back. Right, okay. And what's the momentum change? Well, it started off at that, and then when it stops, its velocity will be equal to 0. So if its momentum is equal to mass times velocity, and velocity is 0, it doesn't matter what the mass is, the momentum is always going to be equal to 0 as well. So what's the change? Well, it's gone from that big number to that little number, so it's just the exact same thing. 970,000 kilogram meters per second is the change. The photograph shows a man dropping an egg inside a padded box from a height. The weight of the egg, weight, is equal to 0.6 newtons. Calculate the work done, energy, on the egg to lift it up by 20 meters. And height is equal to 20 meters. Now, sometimes we're going to get these, but don't panic, because remember that weight is just a force and height is just a distance that goes upwards. So even though we've got W, E, and H, there's no equation linking those two. There is an equation, those three, pardon me, E is equal to F times D. So all I have to do is equal to 0.6 times 20. 0.6 times 20 is equal to 12. Energy is equal to 12 joules. The velocity of the container was 18 meters per second as it hit the floor, 18 meters per second. The mass of the container was 0.5 kilograms. Calculate the momentum of the container, and I don't know how many kilogram meters per second. Momentum is equal to mass times velocity. Momentum is equal to 0.5 times 18. Momentum is equal to 9. I'm not going to do that if you don't mind, folks. Kilogram meters per second. Oh, golly, what if I'm wrong? I know I'm not wrong, but I just had to double check. A man monitors how much money he spends on electricity. He uses a device which calculates the cost of electrical energy used. He connects his power, 2.9 kilowatts, remember, multiply that by 10 to the power of 3 if we want to get it to its base units, to the 230 volt kettle. Main supply, calculate the current in the kettle element, and I don't know how many amps. Power is equal to current multiplied by voltage. I'm going to divide across by V to get power over voltage is equal to current. 2.9 times 10 to the 3 over the voltage, which is 230 volts, will equal to my current. 2.9 times 10 to the power of 3 divided by 230 will equal 12.608. So 12.6087. All right, it doesn't really matter. I'm probably going to return that as it's no decimal places, so I'm going to bring that as 12.6. Don't know why, it just feels right. You could probably do 13 amps as well if you wanted to, just because it's whole numbers, but it's neither here nor there. The device shows that in 1 week, the total cost of the electrical energy used by the kettle is 97p. 1 week equals 97 pence. 1 kilowatt hour of electrical energy costs 17p. Calculate the length of time for which the kettle has been switched on during the week. Okay, pretty sure this isn't on it. But 1 kilowatt hour is equal to 17p. How many bits of 17 go into 97? 97 divided by 17. 97 divided by 17 is equal to, I'll change it, boy, I'll change it, 5.70. 5.70. It's the amount of times it goes into that. This isn't needed. I know we don't need this. Yeah, I feel like I don't want to do this. But it doesn't, yeah, I suppose it doesn't really matter, does it? I need to check this with Mr. Patrick. Right, so basically, it's a 2.9 kilowatt electric kettle. So 1 kilowatt hour costs this amount of much, so it's going to be 2.9 kilowatt hours costing 17p for this electric kettle. So you're going to do 97 divided by 17, and then multiply that by 1 over 2.9, which is going to give you the answer. So just, I don't want you to do this one. Ignore this one. Just we'll skip on to that. Pretty sure it's not part of the maths unit. Resistor is connected to a power supply. If it is, then I'm wrong, and I'll double check that. I'll do a separate video on it, but I've never taught it, so I hope it's not true. I only know it because I pay electricity bills. Resistor is connected to a power supply. The potential difference across the resistor is 6.0 volts. The resistor remains connected for a period of time. The current in the resistor is equal to 200 milliamps. Now I want to make that into its normal unit of amps. So I'm going to divide it by 1,000 or times it by 10 to the minus 3. You can divide it by 10 to the 3 as well if you prefer. But 10 times 10 to the minus 3 is the exact same thing as dividing by 1,000. It's got a total charge of 42 coulombs flowing through resistor. Calculate the time in minutes, sneaky little gremlins, wanting us to get it wrong, checking our units. The amount of time taken for this amount of charge to flow through the resistor. So, we've got Q, we've got I, we've got V. We're going to find out T. Okay, we've got Q, we've got I, we're going to find out T. We're looking for the amount of time in I don't know how many minutes. So the equation is Q is equal to I multiplied by T. And then I'm going to do my rearranging thing. I'm going to divide across by I so that T is by itself. Q is 42 coulombs divided by the amount of current, which is 200 times 10 to the minus 3. And that will equal the amount of time that we've got. 42 divided by 2, 0.2. 42 divided by 2. Okay, sorry. There's someone in here, folks. Gives me two ticks. Pardon me. I'm getting distracted away by something. Yes, that's absolutely fine. Do that. Cool. All right. So this gives me the time in seconds as 210 seconds. No, it's absolutely fine. Don't worry about it. Divide by 60. It gives me, and if I divide that by 60, that will give me my time in minutes. Giving me my time in minutes to be 3.5 seconds. Calculate the total energy transferred by the 6-volt power supply when their charge of 42 coulombs flows through the resistor, and now it's not working. Calculate the energy transferred. It's asking me for E in joules by the 6-volt power supply. Volt equals 6 when there is a charge of 42 coulombs. E is equal to Q times V. E is equal to 42 times 6. 252 is my answer. 252 joules. All right, let's move on. Oh, and it's blocking again. Come back. Please come back. All right. International Space Station has several solar panels called wings. In 1 second, the useful energy available from one wing is 34.3 kilojoules. My word. The energy incident on the wing and the sun is 5 times this, from the sun is 5 this amount. What is the percentage efficiency of the wing? Okay, so in 1 second, it is equal to 34.3 kilojoules. That is the same as 34.3 kilowatts, but that's absolutely fine. So the energy incident on the wing is 5 times this amount. That just means the actual amount of energy that's hitting it so the total amount of energy is 5 times that amount. So it's 34.3 times 5. This is useful energy because it's the amount of energy that we can use in 1 second. If it's asking me to find the efficiency of the wing, I don't know what that is, but I can express it as a percentage or as a decimal point. What do they want? They want it as a percentage. So I shall write down my equation. Efficiency is equal to useful divided by total. Efficiency is equal to 34.3 over 34.3 times 5. The efficiency will then give me a number of 34.3 ABC, 34.3 times 5, 0.2. Now I want this in a percentage, so I'll multiply it by 100, giving me my answer to be 20%. So if they throw funny words at you, ignore the funny words. Just look at what they're asking you. Trolley is attached to a string passing over a pulley. 100-gram metal disc. I'm going to take this. 100 grams. Hangs at the end of the string. The light gate measures the time it takes for the car to pass through it. When the trolley is released, it accelerates along the track. The car takes the time of t is equal to 0.04 seconds to travel through the light gate. The student calculates that the average speed of the trolley through the light gate is 1.15 meters per second. Calculate the width of the car. W equals I don't know how many meters. But we're not looking for width. We're looking for distance because that's what we've got an equation for. Width between 2 points and distance between 2 points, same thing. Speed is equal to the distance divided by the time. Speed is equal to 1.15 divided by 0.04, giving me an answer of 1.15 times 0.04, 0.046 centimeters. Now, is that right? Just having a quick look here, meters per second, 0.046. Is that right? It looks right. Everything seems okay. I don't think anyone's missing. Yeah. Yep, happy with that. Okay. Trolley travels 1.2 meters along the track from the start before the car reaches the light gate. Show the acceleration of the trolley along this distance is approximately 0.55 meters per second squared. Now, unfortunately, we don't have any room to do this one. It's an unfortunate thing, but it is what it is. We're going to have a little look at 0.046. I don't know why I don't like this. 0.046. Ah, look at that. What was I not doing? I wasn't checking my centimeters. All right. So 0.046 centimeters is a tiny fraction of centimeters. It's asking me for my answer in centimeters. I gave its answer in meters. I would have lost the mark there, but I spotted it because it didn't make sense. So what I'm going to do is I'm going to multiply that by 100, giving me my answer is 4.6 centimeters. Because 1 meter is equal to 100 centimeters. I knew there was something wrong there. The trolley travels along 1.2 meters along the track before the car reaches the light gate. Show the acceleration of the trolley along this distance is approximately 0.55 meters per second squared. Right. Okay, so what I'm going to do is I'm going to have to use it's trying to ask me to find the acceleration, and it should be about 0.55 meters per second squared. It has got an end velocity of 1.15 meters per second, and I have to assume that it started off with 0 meters per second because it wasn't moving. The distance that it traveled, the displacement was 1.2 meters, so I can now use my equation A is equal to v minus u, v squared minus u squared equals 2 times a times x to find the acceleration. Oh, come on now. Please, please, please. Okay, so here's my equation I'm using. V squared minus u squared is equal to 2 times a times x. I can rearrange it first, or I can substitute it first. It doesn't really bother me, so let's just do the alternative. We're going to do the 1.15 squared minus 0 squared is equal to 2 times a times the distance, 1.2 meters. I'm going to put this down. I'm going to rearrange it now. Minus 0 squared over 2 times 1.2 is equal to acceleration. 1.15 squared. And I'm even going to write this in. Times 0 squared over 2 times, over. There we go. 2.4. Oh, not letting me do that. I pressed something wrong. Let's try again. 1.15 squared divided by that is equal to 0.55 0.51 meters per second squared is my acceleration. So it did. That's good. Go team. Woohoo. Now it's going to take a bit of time to come back. The car is traveling along a level road. The car now accelerates in a straight line. Calculate its average acceleration is 12 meters per second squared. Calculate the increase of the velocity in the car. So calculate the final velocity, I don't know how many meters per second, in a time that is given to us of 4.0 seconds. Now it was, I don't have you. How am I going to do this if I don't have you? The car is traveling, the car now accelerates in a straight line. Its average acceleration is that. Calculate the increase in velocity of the car in 4 seconds. Okay. I mean, oh, just the increase in velocity. All right, we can do that. All right, so 12 meters per second squared means that every second it's increasing its velocity by 12 meters per second. So after 1 second, it will increase its velocity by 12 meters per second. After 2 seconds, it will be 24 meters per second increase. After 3 seconds, it will be 36 meters per second increase. And after 4 seconds, it will be 48 meters per second increase. So to find this, we just do 12 meters per second squared times 4. That's my answer. Oh, blah 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 blah. I can't put names on the internet, so I really hope that mind you, right, okay, I'm just going to stop. Oh, I hope it didn't. I don't want to do this again.